Our first problem was x squared plus y squared equals 1. Now I hope you recognize that. That's the unit circle. I know we've temporarily skipped the section on circles, but hopefully from your knowledge of trig, you recognize that that was the unit circle. And just looking at the graph, I can see that's got all three types of symmetry. So it's going to be symmetric about the y-axis, the x-axis, and the origin. Let's just really quickly run through that. If I wanted to check about the y-axis, let's just remember that that means if I have a point xy, it's going to see its mirror image over here. And I can see that's going to be at the same height, so same y value, but since it's on the other side of the y-axis, it has the opposite x value. So if I'm supposing that a point xy is on the graph, I'm supposing that x squared plus y squared equals 1 is a true equation. I'm going to see what happens when I replace the x with the opposite of x. So we would get the opposite of x squared plus y squared equals 1. I know even powers are going to just get rid of that negative sign. So that's going to become x squared plus y squared equals 1. And since those equations are the same, the answer is yes, this has symmetry about the y-axis. Okay. If we check the x-axis, our picture is similar, except the mirror image point would be on the other side of the x-axis. So a point xy here, its mirror image would have the same x, but since the point is on the opposite side of the x-axis, would have the opposite y value. So again, supposing that xy is on the graph, that makes this equation true. Is it going to be true if I now replace y with the opposite of y? And when I simplify, even powers are going to get rid of that negative. So these equations are the same. So yes, this has symmetry about the x-axis. Now it turns out, if a graph has symmetry about both axes, it's going to have symmetry about the origin. But do be careful, doesn't work the other way. Remember we said that the graph of y equals x cubed had symmetry about the origin. That does not have symmetry about either axis. But if something has symmetry about both axes, it's going to have symmetry about the origin, because notice, if it's got symmetry about the y-axis, then this point being on the graph means this point is on the graph. But if this point is on the graph, it's going to have a mirror image that would have the same x value, which is the opposite of this x value, but the opposite y value. And that's the point that would be the mirror image about the origin. Okay. So that's a nice shortcut, although it's very quick to check. You would just take this equation and replace both x and y with their opposites. And we saw that the opposite of x squared is just x squared. The opposite of y squared is just y squared. So this has symmetry about the origin as well. All right. For number 2, we're looking at the absolute value of x plus y equals 2. Now when I check for symmetry about the y-axis, again, if a point xy has a mirror image on the other side of the y-axis, the coordinates would be the opposite of x, y. So I'm going to take this x and I'm going to replace it with the opposite of x. Now be very careful here. If I have the absolute value of x, that's the same as the absolute value of the opposite of x. That's definitely true. So for example, the absolute value of 2 is the absolute value of negative 2. Okay. But here, I'm adding y before I take the absolute value. Okay. The absolute value serves like parentheses. It's a grouping symbol. So you do whatever's inside first. And I can't get rid of a negative that only applies to part of the inside. So this is just the opposite of x plus y equals 2. Instead of x plus y, it's essentially y minus x. I've gone from an addition problem to a subtraction problem. If I look at it with some numbers, okay, so certainly it's the case that the absolute value of 1 plus 1 is equal to 2, because I would add them, I would get 2. The absolute value of 2 is 2. If I replace that one with a negative 1, the absolute value doesn't get rid of the negative and then have me add. I have to add first. I would get 0. Absolute value of 0 is 0. That is not the same. Okay. So this is not symmetric about the y-axis. Not y-axis symmetry. Okay. And if I check about the x-axis, now for the x-axis, remember we're looking for a mirror image point on the other side of the x-axis. So in checking for that, I'm replacing y with the opposite of y. So that would become x plus the opposite of y equals 2. Again, I've got to do the arithmetic before I take the absolute value. If you try to get rid of that negative sign, you're taking the absolute value of each piece and then adding. But that would be the absolute value of x plus the absolute value of y, which is very different from the absolute value of x plus y. So, no, that's not the same thing. So there's not symmetry about the x-axis. Now, let's check about the origin. Remember, if we're looking about the origin, a point xy would see its mirror image on the other side, and that's going to have the opposite x and the opposite y value. So, if I replace x with the opposite of x, and I replace y with the opposite of y, now here, since there's a negative sign in both terms, I could factor that out. I could say that's the absolute value of the opposite of x plus y equals 2. Now this negative applies to the whole thing. And we did say that the absolute value of a number is the same as the absolute value of the opposite of that number. Here my number is just x plus y. So now, because the negative applies to the whole thing and not just one part, I can say that this does simplify to the absolute value of x plus y equals 2. That's the same equation. So yes, this does have symmetry about the origin. Notice in the first problem we were able to say, hey, if you're symmetric about both axes, then you're symmetric about the origin. But remember, I said that's not always going to be the case. You could be symmetric about the origin without being symmetric about either axis, and that's what we have in problem 2. Okay, for problem 3, if I check for symmetry about the y-axis, I can say I'm going to replace x with the opposite of x. So that would give me the opposite of x to the 5th minus y squared equals 3. And I was starting with, should have written this first, sorry. I was starting with x to the 5th minus y squared equals 3. That's the equation that's true if a point xy is on the curve. Now, when I replace x with the opposite of x, I get this. And remember, the rule is that odd powers are going to preserve that negative sign. So I'm going to get the opposite of x to the 5th minus y squared equals 3. These are not the same equation, so no, this is not symmetric about the y-axis. Now, if I check for symmetry about the x-axis, the mirror image point about the x-axis would have the opposite, would have the same x value and the opposite y value. So my original equation is x to the 5th minus y squared equals 3. I'm going to replace that y with the opposite of y. Now notice there's still a subtraction sign in between the two terms. Now I'm squaring the opposite of y. But when I square, that's going to eliminate this negative sign. So we'll get x to the fifth minus y squared equals 3. And these equations are the same. So if xy is on the equation, is on the graph, making this equation true, then x negative y is on the graph, making this equation true, because they're the same equation. So this does have symmetry about the x-axis. Does it have symmetry about the origin? And I'm pretty sure the answer is going to be no, because I saw that replacing x with the opposite of x changed this term, but replacing y with the opposite of y did not change this term. So let's just confirm that really quickly. Again, if we're looking at symmetry about the origin, we're saying the mirror image point would be this point here that had both the opposite x and the opposite y value. So we'd be looking at, negative x to the fifth minus negative y squared equals 3. Here, that negative sign is preserved. Here, it's not. These equations are not the same, and so the answer is no, it's not symmetric about the origin. So the first equation had all 3 types of symmetry. The second equation had symmetry just about the origin, and the third equation had symmetry just about the x-axis. All right, in the next video we're going to start talking specifically about functions. And since we'll be talking about functions, we're going to be concerned about symmetry about the y-axis and the origin, but not so much about the x-axis, because as we've discussed, if it's a function, the only sorts of functions that can have symmetry about the x-axis would be functions that are always 0. And those are a little bit boring. So we're going to look at just the 2 types of symmetry that a non-zero function could have, and that's symmetry about the y-axis and the origin.